Hello everyone, my name is Kai Cai. Welcome to this bootcamp for supervisory control of discrete event systems. Supervisory control is an unconventional branch of control theory that addresses control problems at high levels with discrete control strategies. By a bootcamp, my intention is to introduce this theory in a tutorial fashion, and more importantly, to get your hands on a Python software tool from the early stage so that you can code and see the theory in action. Let me start by explaining to you why I'm motivated to design this course. I've been teaching this course for more than 10 years, and there are textbooks for supervisory control, including my own book with Murray Warnham, who is the founder of the theory, and another popular textbook by Cassandros and Lafortune. But these books are big. Ours has nearly 500 pages, and the other one has more than 800 pages. New students have found this existing material daunting. Not just the students. Our colleagues of standard control theory have found the math framework of supervisory control foreign. They often say, and I quote, "There are no ODEs." ODEs are ordinary differential equations, which are foundational models for continuous dynamic systems in standard control. They are right. Supervisory control is not built on ODEs and therefore non-conventional. But if you strip away the appearance and focus on core ideas, the theory is in fact conceptually simple and familiar. The core consists of states, state transitions, which are all very dear to our hearts as control theorists and engineers. So something must be wrong. I tend to think that it is due to the way that we write and teach this theory is pedagogically untasty. And all this has compelled me to design a course that can make supervisory control more accessible and more fun. You may wonder, why not just use standard control for discrete stuff? You would be right to push me on that. Now, standard control is physics obsessed. It is built on the model of ODEs that involve continuous states like speed, temperature, and time-driven state transitions. And the control objective is often to regulate the low-level continuous dynamics of the system so that the states evolve in a desired way. If we take driving a car as an example, cruise control is a standard control problem to regulate the speed of your car at a set point, say 80 kilometers per hour. Things get a little bit different if we consider a route planning and navigation problem for the car. Say you want to drive from your home to a ski resort. I think you can agree with me that just doing the cruise control, keeping your speed of your car at a set point, does not really get you there. This is where supervisory control kicks in. It models logical behaviors of the system using what's called automaton, which is a fancy word originated in ancient Greek, meaning self-moving. Supervisory control deals with discrete states and event-driven state transitions, and its goal is often to manage high-level strategies. So the contrast is obvious. It is continuous low-level signals versus discrete high-level strategies. It is how much gas do I inject to my car versus where should the car go next. Given this characteristic of supervisory control, this theory is also suitable for systems with no physics involved at all and purely discrete. For example, software tools, database systems, communication protocols, and even large language models. You may be wondering why these digital entities are dynamic systems and why do they need control at all? That's a very fair question, and let me address that. Let's take large language model, or LLM, as an example. You can think of your experience of using ChatGPT. Basically, it's you type something, the LLM replies something. What you typed is called a prompt, which is an input to the LLM. It's just a sequence of words, and inside LLM, it first maps the sequence of words into a sequence of tokens, just some numbers. And this is the initial state of LLM. What happens then is that the LLM selects the next token based on a probability distribution that can be computed based on parameters learned at an earlier training stage. What we are talking now is called the inference stage of LLM. So the internal state of the LLM represents the sequence of tokens that has been generated so far, and state transition is triggered by the event that the LLM has selected the next token. This process of next token generation continues until a complete text is generated as the output of the LLM. So from this perspective, LLMs can be reasonably viewed as having discrete states and event-driven transitions. So it's a discrete event system. Now, are there any control problems in LLMs that need to be resolved? Yes, there are many. One such example is we don't want the LLMs to generate languages that are potentially violent or biased. This can be formulated as a logical control specification, and we want to design suitable controllers that can restrict the behavior of the LLMs such that the specification is satisfied, say by blocking the generated violent languages. So this is where supervisory control can really shine, whereas standard control is out of question because there are no ODEs. Now let's recap the motivations and the importance that you may want to consider learning supervisory control. If you are going to develop digital systems, from software tools, databases, to large language models that can be certified to satisfy desired logical specifications, you should care about learning supervisory control. If you will be developing autonomous physical systems like robot, drones, self-driving cars, and vessels that need to accomplish high-level missions and tasks, you should care about learning supervisory control. Moreover, one of the most exciting cutting-edge research areas actually combines these two worlds, called AI physical systems, or physical AI. These are physical systems controlled by AI algorithms, or put it another way, AI gets its physical body. So it's extremely crucial to ensure that these systems operate safely in the real world. To achieve this, it's my belief and projection that supervisory control will play a key role in developing safety-assured AI physical systems. And this gives you another reason to care about learning the theory. So what you will learn in this course? First, you will learn how to model a discrete event system using automaton. You will then learn how to analyze several key properties of DES, such as reachability and non-blocking. After that, you will learn how to design feedback control for DES, where discrete event version of controllability is central. This is a standard agenda to learn a control theory, and you will see most, if not all, the concepts are familiar. Along with the proceedings, you will learn how to code up everything so that you can get a tangible feel of the theory and see how the analysis and control design can be done and automated with codes. Just a few important historical notes to understand where these are all coming from. The supervisory control was pioneered by Peter Ramage and Murray Warnham in the early 1980s at the University of Toronto. The theory was developed in Peter Ramage's PhD thesis, and his advisor was Murray Warnham. Back then, more and more complicated computer systems had been developed, and the original motivation for the two was the need and the lack of a control theory for computer systems. The term supervisory control was deliberately coined to mean that a control action is inserted only when it is necessary. So this is in contrast with constant actuation as in standard control. In this sense, supervisory control is a form of minimum intervention or maximum freedom for the systems being controlled. So you are all invited to join this bootcamp for supervisory control of discrete event systems. We are going to take a familiar state-based perspective that makes the framework and math accessible. This bootcamp is accompanied by this little book of 113 pages that you can download for free from this website. More importantly, you will get to see the theory in action with our open source software tool, PyTCT, that you can download, install, and play with it. So with that, thank you for tuning in, and see you in the lectures. Finally, let me share this information that I will be teaching this course in person, in Paris, and during the week that spans the end of June and the beginning of July 2026. This is a part of the International Graduate School on Control, the 2026 program organized by the European Embedded Control Institute. So if you want to join us in the classroom, please check out this website and register yourself for the course. I'm sure you will have a different experience through our in-person interactions. Thank you.